Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3. Then today we will present about the steam methane reformer SMR for this subject. Okay, then we move to the next slide. Okay, this is our group members. First is Aisyah binti Abdul Wahab, then Ahmad Shah binti Ejisur Rahman, then Nur Shazwina binti Muhammad Sabri, then Nur Atirah binti Abdul Munir, and lastly is me, Muhammad Arif Iskandar bin Awang Zali. Okay, then we move to the project executive summary. Okay, this project is focused on design and simulation of a hydrogen production system using the steam methane reforming SMR process. SMR selected due to its high efficiency, technological maturity, and economic feasibility for large-scale hydrogen production. Process simulation carried out using Aspen Plus under industrial operating condition. Key units, model, fits, preparation, steam methane reformer, water gas shift reactor, condensation, and flash separation. Analysis includes mass and energy balance, component compensation, and hydrogen yields. Effect of operating parameters such as temperature and pressure of hydrogen production. Project strength as understanding of SMR technology and practical skill in process simulation and engineering design. AutoCAD is used to develop isometric assembly and dimension drawing of the steam reformer. Okay, now we move to the introduction. Hydrogen is a key energy carrier in the global shift towards a low carbon and sustainable energy system due to its high energy density, clean combustion, and role in reducing greenhouse gas emissions. Hydrogen is widely used in industrial applications such as ammonia synthesis, petroleum refining, methanol production, fuel cell, transportation, power generation, and system storage. Currently, more than 65% of global hydrogen production is fossil fuel-based, with steam methane reforming being the most widely used method due to its high efficiency and low cost. Hydrogen must be produced from other resources, and various production routes exist, including steam methane reforming, coal and biomass gasification, water electrolysis, and chemical water splitting. Despite the growth of renewable-based hydrogen technologies, SMR remains the industrial and economic benchmark for hydrogen production. As we can see the figure I put there, hydrogen production routes, steam methane forming natural gas can produce hydrogen and carbon dioxide. Then coal gasification, coal which is can produce hydrogen and carbon dioxide. Water is also the same, but have the add-on from the hydrogen and electricity, which is can produce hydrogen and oxygen. Then chemical photochemical splitting also can produce the same product, which is hydrogen. And then for the steam methane forming FMR process, which is catalytic process converting methane to H4 plus steam H2O, then can produce hydrogen. The main reaction is primarily reforming endothermic. Methane plus water can produce COO and H2. Then water gas shift, which is carbon monoxide plus water can produce carbon dioxide and hydrogen. Then industry importance and advantage. Most mature and commercially viable hydrogen production technology and hydrogen reliable operation will understood kinetic, compatible with large-scale continuous production and can be optimized using Aspen Plus for mass or energy balance reactor for performance and process efficiency. Then environmental condensation and challenge. Significant CO2 emission from reforming water gas shift reaction, carbon capture storage CCS can reduce emission to blue hydrogen. Then scope and relevance of project, which is SMR chosen for industrial relevance and technological maturity and aims to improve understanding of hydrogen production and application of CAD and simulation tools in chemical. Project include development of SMR process flow diagram, simulation using SCOM Plus, and equipment design using AutoCAD.
Assalamualaikum, good day everyone. Today I will briefly explain about the steam methane reforming process flow diagram and the AutoCAD drawing with detailed dimensions of the steam reformer, which are essential components of process simulation and computer-aided design in chemical engineering. First, let me explain about the steam methane reforming SMR process flow diagram. The process starts with natural gas, which is first sent to a desulfurization unit. This step is critical because sulfur compounds can poison the catalyst used later in the reformer. After desulfurization, the clean natural gas is mixed with steam in the steam mixing unit. The steam methane mixture then enters the steam methane reformer furnace, where it reacts at high temperature in the presence of the catalyst. In this step, methane reacts with steam to produce hydrogen, carbon monoxide, and carbon dioxide. The reformed gas then passes through a water-gas shift reactor where carbon monoxide is converted into additional hydrogen by reacting with steam. Next, the gas is cooled and condensed to remove excess water. Finally, the hydrogen-rich gas enters the PSA purification unit, which separates hydrogen from other gases, producing high-purity hydrogen as a final product. This flow diagram clearly shows how each unit operation is interconnected, which is very important for process simulation studies. Huh? Tak record ke? AutoCAD drawing with detailed dimensions. This drawing represents the assembly of the steam reformer, including multiple reformer tubes arranged inside the furnace. The orthographic views and the 3D isometric view help us visualize the physical layout, tube spacing, height, and base dimensions. These dimensions are crucial for equipment sizing, layout planning, and simulation accuracy. In conclusion, the process flow diagram helps us understand the chemical and operational sequence, while the AutoCAD drawing translates the process into a realistic mechanical design. Together, they demonstrate how computer-aided tools support both process simulation and equipment decision, which are key learning outcomes of this course. Thank you.
Okay, Assalamualaikum. My name is Aisha binti Abdul Wahab, KH23012, and today I will be presenting the steam reformer drawing starting from the hand sketch to the AutoCAD and assembly drawing. For first figure, show the hand sketch drawing of the steam reformer. This initial sketch was prepared to visualize the overall structure and internal arrangement of the reformer. It helps in understanding the positioning of the reforming tube, burner placement, and general flow path before converting the design into technical drawing. For the second figure, it represents the AutoCAD drawing of the steam reformer. The hand sketch was refined using AutoCAD to improve accuracy, proportion, and clarity. This drawing provides a more precise representation of the reformer geometry, making it suitable for technical reference and further design development. And the last figure shows the part and assembly drawing of the steam reformer. The main components are labeled, which include the burner, reforming tubes, and flue gas tunnel. The burner supplies heat required for the endothermic steam methane reforming reaction, and the reforming tubes contain the catalyst where methane reacts with steam to produce hydrogen and carbon monoxide. The flue gas tunnel allows hot combustion gases to flow around the tubes, ensuring efficient heat transfer. And in conclusion, the hand sketch helps in conceptual design, the AutoCAD drawing improves technical accuracy, and the assembly drawing clearly illustrates the components and their function within the steam reformer system.
Assalamualaikum, my name is Ahmad Shah bin Najisur Rahman and my metric number is KH23013. So my part, I work on simulating SMR process using SMR+. So my process flow and all design parameters were extracted using two references. First one is Ohly 2024 and Molbert Doctor 2003. So from Oh and Lee 2024, I referred their Aspen simulation SMR process where they use SRK property method, soft red list quang. This model accurately represents gas mixture containing CH4, H2, CO, CO2 and H2O. The same component involved in both steam reforming and water shift reaction. It was chosen because it performed well under high temperature, high pressure, non-polar gas system, which is exact the condition of SMR and WGS. Meanwhile, in other reference, Molbert and Dr. 2003 provide the industrial scale operating data for the production. So the reactor temperature and setting, which I use as the basis for this model, which is 850 Celsius and 25 bar for the reforming reactor, while at 425 bar, 400 Celsius and 25 bar for the water gas shift reactor. So this process contains 5 main blocks. The first one is mixer. So it combines the methane and steam H2O feed at ratio 1:3 molar ratio. This ratio prevents carbon deposition and ensure complete methane reforming. The second is R1, which is SMR reactor. So the model I use here is R equilibrium reactor, which set to the 850 Celsius and 25 bar. So this reactor represent the steam methane reforming reaction. So the third is R2WJS. Also model I use is R equilibrium reactor and operate at 400 Celsius and 25 bar, representing the exothermic reaction, shift reaction. So this number 4 is cooler. Its function is to cool gas temperature to around 35 Celsius for condensation. And lastly is separator. The model I use here is Flash 2, and it functions to separate and cool gas into the vapor stream rich in hydrogen and liquid stream containing condensed water and CO2. Next, I will continue how actually the process basically works. So CH4 and also H2O feed will enter at the mixer, and also it will form into the single combined stream. Then the mixer stream enter the first reactor R1 where SMR occur. The methane react with steam to produce CO and also H2. Because SMR is endothermic, the methane conversion is high at 850 Celsius, but CO still remain in the outlet gas. Then the outlet gas from the reformer goes into the R2WGS reactor, where the remaining CO react with the steam to form CO2 and more hydrogen. After that, the gas is cooled and sent to the flash separator. The vapor outlet at the top contain hydrogen, while the liquid outlet at the bottom contain mainly water and also some dissolved CO2. So now by looking at my experiment result, at the mixer outlet, the feed contain 25 kmol per hour of CH4 and 75 kmol per hour of H2O. After enter reformer R1, methane conversion is almost complete, where CH4 decrease from 25 to nearly 0 to produce CO about 25 kmol per hour and H2 reach around 75 kmol per hour. This confirms the successful endothermic SMR reaction. Then, after enter the WGS reactor R2, CO decrease from 25 to 60 kmol per hour, while CO2 increased to about 8.6 kmol per hour, and hydrogen rose up to approximately 83.7 kmol per hour. These results show that the water gas shift effectively converts CO to CO2 while generating additional H2. After cooling, it will enter the separator. The gas phase at the top and hydrogen rich with mole fraction about 0.76, while the liquid phase at the bottom mostly condensed H2O and CO2. That's all from me. Thank you.
My name is Nur Atira binti Abdul Munir, KH23028. So today I will talk about the effect of operating temperature. So operating temperature is very important in steam methane reforming and the water gas shift reaction. In steam methane reforming or SMR, methane reacts with steam at a very high temperature, usually between 700 and 1000 degrees Celsius. So at this project, we used to 850 degrees Celsius. So because this reaction is endothermic, higher temperature provides the energy needed for the reaction to take place, which leads to the higher methane conversion and more hydrogen being produced. If the temperature is too low, the reaction becomes slow and less methane is converted, so hydrogen production decreases. On the other hand, operating at extremely high temperature requires more energy and can cause damage to the catalyst and reactor materials due to the thermal stress. After the deforming step, the water gas shift reaction is used to convert carbon monoxide into additional hydrogen. This reaction is exothermic, meaning that lower temperature helps hydrogen formation, while higher temperature helps the reaction proceed faster. Because of this, the shift reaction is operated at control temperature to balance reaction speed and equilibrium. Overall, maintaining proper temperature control throughout the SMR process is essential to maximize hydrogen production and ensure high product purity. So next, the effect of operating pressure. So operating pressure plays an important role in steam methane reforming and the water gas shift reaction also. So in steam methane reforming, methane reacts with steam to produce hydrogen and carbon monoxide, and this reaction creates more gas molecules and on the product side. So because of this, when the pressure is increased, the equilibrium shift backs toward the reactant, which lower methane's conversion and reduce hydrogen production. So this is why lower pressure are generally more favorable for producing hydrogen. However, operating at high pressure also has a practical benefits, which is higher pressure allows the use of smaller reactor, improve heat transfer and makes hydrogen purification more efficient, especially when pressure swing adsorption or PSA is used. For the water gas shift reaction, pressure doesn't greatly affect the equilibrium because of the total number of gas molecules stays almost the same, but higher pressure can still help improve reaction rates and overall process integration. So as a result, industrial SMR plants usually operate at moderate pressure. This allows them to balance hydrogen production with efficient equipment design and effective downstream purification. So that's all from me.
Okay, then now we move to the last part of this presentation, which is conclusion and explanation. For conclusion, this project is successfully designed and implemented a nitrogen production process based on steam methane reforming SMR using SMR and TOCAD. High reformer temperature significantly increase methane conversion of hydrogen yeast, and operating pressure requires a balance between thermodynamic efficiency and downstream process performance. Simulation results align well with industrial data and literature, validating model reliability, AutoCAD drawing, improve understanding of equipment, geometry, assembly, and plan layout. Then for the recommendation, we also have a three-part, which is the first, incorporate ripple reaction, kinetic and catalyst performance model in S4 Plus and include reaction through effect and advanced heat integration analysis. Then second is expand environmental assessment by integrating carbon capture and storage CCS for low carbon blue hydrogen production. Then lastly is conduct life cycle assessment LCA to evaluate environmental impact and emission. Okay, that's all from our group. Thank you for hearing our presentation. Thank you.